We were talking about the Gaussian mixture models last week, on Tuesday, and we were talking about k-means clustering before that, which was a simplified version. So the reason why we introduced the Gaussian mixture models was to have a probabilistic model which is more powerful in the sense that it will have a soft assignment, and also more powerful in terms of the shapes that you can use to match your data. So these are some important unsupervised learning methods which you want to discuss. And then we moved to this chapter, the EM algorithm, which is just the algorithm to solve all this. So what is the algorithm to solve this fitting problem of finding the best generative model which explains the data, so which maximizes the likelihood of your data if you assume that you have a Gaussian mixture model, for example, but we will see today that it's actually much more general, can also be used to solve more generic problems. So that was where we kind of stopped last time, that we asked them, how can we maximize the likelihood of a Gaussian mixture model? We said we want to do it incrementally. We want to do it so step by step by starting somewhere. Theta again consists of all these parameters of our generative model which you want to learn. So there are three kinds of them. The most obvious one are these mu's, which you have one per cluster. The other one is the sigma, which you also have one per cluster, but sigma is actually a matrix for each cluster, which is the covariance matrix. And then there was the last parameter, which was the pi's, which is just one number per cluster. So these are the parameters we're gonna learn. So this theta vector here. Okay, and how do we do this? So we want to find the best theta, but that's too hard. So we will just start somewhere and take an approximation there. So where were we? We were trying to motivate this iterative procedure to find the parameters for our model. We said we start somewhere, we want to optimize the green function, which is too hard. Therefore, we just build a small surrogate model, which is a much easier model to optimize. So that's this one. We maximize that one, so which brings us here. And that's our next iterate of our parameters. It's not the perfect one, right? But it's hopefully a better one because the surrogate model brought us a little bit higher. So then we're here, and again, we do the same thing. We will repeat by building a surrogate model. That's the so-called expectation step, as you're going to see. And then we will gonna maximize that surrogate model, which brings us here to the next step. That's the so-called maximization step. So yeah, don't hesitate to ask questions anytime, also on Zoom. So I think the algorithm generically is quite simple. But what it's not so simple is how exactly is this surrogate model defined, right? And also how are we going to do the maximization? That might depend a bit. So it's gonna all depend on what's the surrogate L with a bar below it, and that's what we're going to discuss today. I hope that's clear. So that's our goal, and let's see what we can do here. Okay, so the first thing we want to discuss is how to define the surrogate, and that will go a bit together with showing that it's actually below our function. And so, and it's okay. Let's do this step by step. So what we have on the left here is actually, that's our original function. That's why it was always green, right? But this is only the L for one data point. So that's our original function. If you go back here, then you see there was the L, but L was sum over everybody. But so the Ln is just how good is our fit for the one data point, right? So this is Ln, and L is the sum of all the n's, of course, all data. So okay, so what we're going to do is we build a surrogate which is lower than Ln and touches it at the current point. That's our goal. Okay, so here is Ln. What's going to be the surrogate? It's going to be this thing here. And why is it a surrogate? Because we say that we are claiming that here. So this is a lower bound on ln, right? And so, and this thing will be our surrogate function. So we define this to be the L with the bar under it. So this is the lower bound. So that's the name we give it. And that depends on a few things. It depends on where you define it. And yes, that's it. Okay, so now this is completely out of the blue. I didn't explain you why it's a lower bound and why this is a good choice. So why is this a lower bound? And to do this, we just, that's actually what we said at the very end on Tuesday. We said that actually, yeah, if the problem is that there's this logarithm between the two sums, which makes things extremely strange how they interact with each other. If we said that if this would not be there, if there was a linear structure, that would be much easier, then we could actually decouple everything. And so if the log would be linear, then things would be fine. And that's what actually happens here. We actually use a trick to treat this logarithm a bit as if it were a linear thing. But what do I mean by that? What we will actually use is what is called, well, convexity. And maybe those of you, some of you also might have heard of Jenkins Inequality. So I will explain what that means. But the point is that the log function is a nonlinear function. So it's a bit a tricky function. And what I want to do is I want to use convexity of this function, actually convexity of minus the log, which is the same thing as concavity of the log. So that's what we're going to use. It looks a bit scary in terms of formula, but it's very simple. So we will see in a second. So I will just use the convexity of the minus log. So maybe it's best explained in a picture. So, okay. Green is the function here. Sorry that the slides are a bit frozen on Zoom. We will be back soon. So, but the logarithm looks a bit like this. It's a concave function, right? And what concave means is, I will just plug in the definition. Sorry. For the, yeah, and as a backup for people on Zoom, we always have the slides behind me. Just need to move away. Okay, so concavity here, what does it mean? It means that the function between any 2 points is like above the linearization. So the dotted line here is the linearization between 2 points, right? And these 2 points we call R1 and R2. And then we ask that the function is above the linearization. So that's here. So you go somewhere in the middle, right? And you ask that the true function is above the linearization when taken at the convex combination of the points. So this here is a convex combination of the R points. And I'm just doing this so you get the right notation that we also use in our special case, right? So the convex combination would be some weights of these R's, and the weights we actually call Q. Okay, so that's what is happening here. That's what this inequality means, and also some of you know this. This is also just equivalent to Jenkins inequality. right? If you just do this for 2 points, then it's convexity. And if you do it for k points, then it's Jenkin's inequality. So, but we know that Jenkin's inequality is always true for convex functions, or here it's true for minus the log, which is a convex function. So we can always use this property. This is true for any points r. It doesn't. They can be anywhere you want the r values, and the q's as well. But the q's need to sum up to 1. So does this make sense? So for any weights q convex combination, right? For any such convex combination, this is true. The two functions above. So we can use that. And okay, what are we going to do in our case? So I want to convince you that this is our lower bound. It's our surrogate function. So I have q's and I have r, but I haven't specified them. So I will say that this will be my q and this will be my r. That's what we're going to do. So and yeah, that was a bit fast. So let's try to verify that the q's and the r's, what they really are in this case. But again, we can set them to anything as long as the q's sum up to 1. So yeah, first this one. That's going to be my r thing. Okay, and then what we have here on the left side, right? This must be the sum of the convex combination. So this must be qk times r k. Hopefully we will verify this, and then here is your q. I hope this makes sense. And let me know if there are any questions on this. So this is the q here, of course. Sorry. Yeah, question? So.
What is the theta t in our case? Because theta in our case are the mean and the covariance matrices. What is the theta versus the theta t? Because I only see.
Yeah, that's a very good point, and I will get right to this. So far we only have these parameters, right? But you're right. I need to, if I define this lower bound, I need to be very precise. I want to define it at theta t. So at the one parameter that is fixed, and then the surrogate thing, of course, is a function. So yeah, very valid question. What is this second thing here, theta t? And I will do this right now. So that's the theta t is, let's do this in red. So it's here, right? So this is crucial. So let's try to, and again, this will have like 3 components. So we need to be, whenever I write mu or whatever, I need to be clear if I mean the mu from here or the mu from there, right? That's what I'm missing, and you are completely right. So I want to have the q's, these convex combination weights. Those are the ones where you have defined your model. So those are from theta t. So this q will be from the parameter at time t, and the others are free. So the others are the blue stuff. So which we optimize, right? So that's the blue stuff. Yes. Does that make sense? Okay, so it's, yeah.
QKN and QK.
What is QKN? Yes, this I also need to talk more precisely. We will get to this. And yeah, actually, in reality, there's only this QKN, right? So we do this for every point n separately. So there's only QKN. So what was here is just an illustration. This is just for convexity. Yeah, if you want, you can call these guys here also. Here you can also call it QKN. This is just for illustration, right? What have we used? We have used convexity of log. But then in reality, here is how we do it. We use QKN, very important what you said, that yes, those Qs are defined at parameters time t. So this comes from the red stuff. So yes, so what are these Qs? So Q, Kn. Here's what they are. They are just some kind of average of the probability of your current data point. Sorry, the probability of your current data point when it's assigned to cluster K. So yeah, because it depends on both your n and also whatever K you ask for. So they depend on many things. And yeah, sorry, this is not so clear why it's chosen like this. And I will get back to this. Why the QKNs are what they are here. But if you plug it in, then you will see that this is correct. So just plug in this choice of these convex combination weights, put it here and here, and then you will see that yes, I mean, of course, this is a valid choice because the Q's sum up to 1. So this inequality is going to hold and things are fine, right? I mean, I could choose other things for QK. As long as it's sum up to 1, everything is fine. So why this is a particularly interesting choice is actually, we're going to see that later. It's particularly interesting that if you choose this one, then you will get an equality at the current parameter theta t. So, but that's the second property we were claiming here, right? We were saying, yeah, it's a lower bound, and the second property that, yeah, it's actually equal at, if you ask here at the current point. So that's what I'm trying to show you next, that yeah, they are actually equal at where you currently are. So yeah, property 1 is, or property A is this kind of lower bound, and B is showing that it's equal at the current point. So the property A, I think we have shown. Now, okay, so A, we have convinced ourselves that A is true, right? That it's a lower bound. We have just used convexity, nothing special. And now B is this equality, right? So why is this an equality when we ask about particular parameters? So, and okay, so let me try to write this down. What I'm claiming here is that so I take my surrogate model Ln, I plug in I ask actually at the current point, and of course the surrogate model is built at the current point as well, but I'm evaluating it at the current point. So, and what I'm asking is this or not, is this equal to the original function, which is green usually. So Ln of theta t, right? So that's my question. And let's see, we can easily compute that. So what I will do is I will just plug in this surrogate model here. I will see, and I will plug in the special choice here of the current point, see what happens. So it's a sum over these QKs, and then there's a log of stuff. So let's write that. So it's a sum of Ks. And yeah, these are the QKNs of T times the log of this big thing here. I don't want to write it. So what I want to do now is I want to plug in my definition of the QK and see what happens. So definition of the Qs was that it's normal distribution weighted with pi k. So pi k normal distribution. I'm just plugging in this formula into here. So of my point being normal distributed around cluster K. All right. And then divided by just summing everything, by just normalizing. Normalization constant is always important, right? And maybe here I will call this K prime to, I need a different K because here I want to sum up again over all classes. So K prime and again the normalized stuff. Okay, that's the Q. And now I need to write the log of this stuff. Big logarithm. So this stuff here I will just copy. It doesn't depend on the Q. So normal distribution. Okay, and now it gets interesting. Now I divide by this Q. So I plug in what is Q K N. And this is K prime normalizing. Okay, sorry, this is a little bit ugly, but what's okay. What I want you to observe is just that the terms are actually the same. This is the same as this. So I just plugged into this particular Q, right? And I saw that the numerator is the same as the denominator, but there is the additional normalization, so that does not disappear. But the two terms here, they cancel. So this one cancels this one. That's what I'm saying. And this one remains. And what's happening here, we will see. Okay. Yes, we are good. So just we need to be a little bit careful with the K primes and so on. So the stuff, of course. So here we talk about the K outside, right? And then inside we have the K primes, which are when I have this additional sum here. So what we canceled here, that has depended on K. So, and that's actually very nice because now that the term here does not depend on K anymore. So do you agree with that? Because this is only the additional sum of all classes, right? This is the K prime sum. So whatever is in this log is remaining. It does not depend on K anymore. Does not, yeah, so that's really nice. Because it does not depend on K, this thing is actually a constant. So I can take it out of the sum. So I will take this and move it all the way in front of the sum. And what I then have is actually just the stuff which is in red at the very bottom. So that's what's remaining here. Actually the log of the pi, sorry, the log of the sum of the pi k over k prime. So sorry, need to work on the handwriting. So sum over k prime of these weights, k normal distribution x mu k sigma k. And these are all k primes here. Sorry. We're almost there. Don't stay with me for 1 second. It will clean up in a second. So, okay. So this stuff here, this is the red term which has remained. It comes from here, and then this stuff here is interesting. What about this? So Anyone tell me? Yes, you are saying that you are just telling me that this thing is 1, which is true, yeah, because this thing here is exactly the same as the sum on the bottom. So yes, this green term is just 1. So times 1. So we're good. And okay, so what is remaining here? This looks a bit familiar. I just wrote it very ugly, but you have seen this term before, this one. And you have seen it. It is actually ln. Okay, and that's what we claim. So we have shown that this thing is equal to what it should be. We have shown that the surrogate at this same point taken, at the point where it's taken, it coincides with the original function ln. So that's what we have shown here. And this is because we have chosen this particularly smart convex combination weights. You can choose any other ones, right? And maybe there's other ways to make that equal. Of course, you can define other surrogates. I'm just telling you that this particular surrogate has this property. And yeah, that's all we need. So we have shown that it's equal with L. And we have also shown that it's always a lower bound to the true function. So that's good enough for us now. Of course, you could do this with other surrogates. Maybe you're interested to build linear surrogates or anything. But this one is not a linear one, right? It's a bit a more complex function. But it's a nice one, as we're going to see. It will be quite easy actually to maximize this thing. But so far this is just half the work. So to define the surrogate, then the other half of the work will be to maximize the surrogate, the so-called maximization step. Okay, but would you agree with me that it coincides and that it's a lower bound, or any question on any of these two aspects? Yeah.
Question about since you're writing red, why the Q we have a little T after?
You mean this? You mean the Q here, QT. So why does this have the T, the time index? And this is because this is the Q which comes from here. It becomes from where the surrogate is defined. And this thing has 3 parts. You can see here what the 3 parts are. So the 3 parts are what, still the mu, the sigma, and the pi. So all of those are present in this parameter theta t. So they are present there. So I mean, you could use a Q defined on the other guys here, but that's not what we do. So it's quite important that we have chosen the Q defined at Qt. So also when we did this argument here, right? So we have actually, when we plugged in the Qs, I have plugged in what I mean is always that these guys are from the Q, are from parameter t at time t. So yeah, if those are all taken at parameter t. So yeah. So that's important. Maybe I write it in red, right? So Q is always defined at time t. Okay, I'll try to rewrite this a bit in nicer writing later, but any other question on it? All right, so this is building the surrogate. And then let's see what else can we do. So now let's see if you can actually maximize it. So remember, so now you can forget the proof, of course. The only thing you need to remember what the surrogate is. So it's these Qs and the log. So okay, so here it is again. I'm claiming that this is, so now it already looks confusing. So what I'm claiming is that this was the surrogate. So this was a ln bar taken at theta and define that theta t. And again, you see that the q is the one from the parameters time t, so that's crucial. Okay. Yeah, why is this the same function? It looks a bit different than what we had before. But it is the same. So because the q so far looks good, the log we also have, but this looks a bit strange. So what we have done here is that just the log of the two things. There was a log of a quotient, right? And the log of a quotient has been replaced by the difference of the logs. So what we have here is actually equal to the log of the quotient. So okay. And then it's divided by these q guys, q, k, n. Q, again, taking time t. Yeah, so just to verify, yes, this is the same term. So so far nothing has happened. So what I have done here is just I have written all the surrogates and I've summed them up, and I have written that now I want to maximize them. So I want to maximize the parameters of this stuff. One second. So yeah, now I'm getting I'm missing the dividing by q here, right? And maybe you're also missing that. So we got this guy and we got this one, but where is the q here in the denominator? That has disappeared, and that indeed is puzzling. But the trick is, maybe that's what you're going to say, because this q here in the denominator, it does not depend on the parameter, so that's why we can remove it. But it's actually there. So there is a log q, k, n, t here, which also belongs to this term. So, and then all this together is the correct term. Was that your question?
That was a remark. I just think it's too constant, so we can remove it.
Exactly. You're saying it's constant, so we can remove it from the maximization, and that's exactly why I was confused, and that's exactly why this guy is disappearing, right? So you can see, yeah, qt, it depends on the qt stuff, right? That's also relating to your question, right? Where is it defined? The surrogate is defined. So that's coming from this second part. So, and that does not depend on the blue parameters at all. So that's why it's a constant. It's constant in the theta parameters. And theta, I mean the blue ones, right? So does this make sense? So I have removed this third term, which is the guy on the bottom here, because it's constant. And then this one and this one we have kept. So this is the first log and the second log. And yeah, you can see this one is a plus because it was multiplied, and this one is a minus because it was in the denominator. Yeah, this is correct. Yeah. Why don't we remove this qk here? Good question. So you're right that this one does not depend on sigma, on parameters. That's correct. But the problem is the others do, right? This stuff does. So it's a constant, and it's multiplied with stuff which depends on the blue parameter. So and it's just that, yeah, this thing is a bit different for every k you ask, right? And here it's summed up for every n, every k. So this is a constant we need to keep. It's not a, yeah, it is independent of the blue stuff, but it is getting multiplied with different blue stuff. So we need to keep it. I cannot remove this one. But the last one, oh yeah, the last one which we erased. So I mean, that guy was also multiplied with this, but then it's two guys which are independent of parameters. Then I don't need it, right? But here it's one which is independent and one which is dependent on the blue. That's why we need to keep it. So sorry for the ugly writing, and thanks for the question. Okay, so this looks a bit nasty, but again, it's going to clear up. It's not so bad. Well, why am I doing this anyway? I'm just trying. I want to maximize this surrogate, and I'm decomposing it a little bit to show you that it's easier. And because we have got rid of this term, it's a bit easier. So now our goal is just to find the blue parameters theta which maximize this part, and that is actually doable. So there's three things which we need to optimize: the pi, sigma, and mu. Let's do it step by step. So for optimizing the mu's, it's actually, so it's kind of a nice optimization problem. It looks unconstrained so far. So I will just do the standard trick and say, okay, I say at the optimum, the derivative with respect to my variable is probably going to be 0. Yeah, it must be 0. So that's what I'm going to claim. So I'm going to say gradient of my function here with respect to the mu part of my variables, mu, yeah, all the mu's or the current mu k, whatever, for any mu variable. The surrogate will have a derivative of 0. Is 0. Okay, and then we can compute it. It's not so hard. So where is mu? It only appears here. So that seems okay. And then I need to use a bit what is a normal variable, right? So I will just plug in the definition of the normal distribution. And then from that, it's okay to take the derivative. So normal distribution of x given mu and sigma. What is that? So we know this well, right? It's e to the minus x minus mu, and then the covariance comes. It's actually the inverse of the covariance. And then comes again x minus mu. So it's centered at mu, right? So this is the normal distribution. And yeah, from this thing, you can take the derivative. It's not too hard. So, I mean, it's a bit annoying because we're asking for a vector derivative here. So all the mu's. So if the sigma is not there, then it's super easy because then this thing here is just becoming x minus mu squared, the distance. So that's the spherical case. Actually, you will see later that if you do this, then you will recover k-means. So if the probability distribution of one cluster is spherical, like here, you will see that the EM algorithm actually will give you k-means. That's a spoiler alert for later. But that's just because this term you know, right? You remember it from k-means. And taking the derivative of this, we also know how to do. And now it's a bit nastier because now there's a sigma covariance here as well. So here you need to believe me that I'm also able to take the derivative of that object here, which is a bit more annoying. But the one with respect to mu is nice, right? So okay, so what I'm claiming here is that if you do the derivative with respect to mu, so that's coming from here. This you can ignore if you just ask about mu. Then my claim is that this is a solution. The mean actually becomes a weighted combination of the data. And the weights, interestingly, happen to be the Q's, which depend on the current time step where we have defined the surrogate. So I'm not going to do the full derivation of this gradient. You can do it if you have a spare minute. I highly recommend. If you set it to 0, for which mu is it is this going to be 0, then this is what you get. So it's a nice update. And again, this reminds you very much of k-means, because it k-means we would just take the mean of everybody. So there we actually had the assignments right here, the hard assignment. So every x was assigned to one cluster. So now here we have something a bit more strange. We have numbers q, k, n, which we don't know yet what they mean, right? But it's the ones which I've used to define our surrogate, and they appear here again. So they give us an update how we should change our mean to become better on maximizing this surrogate, right? Well, that's all we want to do. We just want to get to the. So now we have defined the surrogate. Now I just want to get to the top point of the surrogate. That's what we're doing now. And I've shown you now what is this top point in terms of mu, and then we'll also do it for sigma and for pi. Okay, so that was for mu. For sigma, we're going to do the same thing. Just set the sigma derivative to 0. So gradient of the same function again, of our surrogate function with respect to now the sigma variable. And here I need to be completely honest that I take the derivative is to the inverse covariance, because that's the matrix I see appearing here. So it's about the inverse. And again, of the same surrogate. And I again set it to 0. And this is a bit a computation, but again, so here you have to believe me that the result of this computation is going to be that the sigma will update as this. And yeah, what is this? So sigma is the covariance matrix, right? So there's no inverse anymore here. So this is about the true sigma. And what is it? So this is it's an interesting matrix here. It's kind of a rank 1 matrix, which it's then for every data point you have this rank 1 matrix. And with that, I mean, almost done in 30 seconds. So this matrix here is a rank 1 matrix. A column vector multiplied by a row vector, V, and so yeah, V is just x minus mu. Okay, that's interesting. So there's this matrix which happens here. Every data point gives you an update here. It's a bit unclear why this is the correct update, but it's certainly easy to compute, right? Just for every data point you compute this, how far is it from card center, and then you build the outer product, gives you rank 1 matrix, and then you just sum up these up of all data points, and we claim that this is now a better covariance matrix. Actually, we claim that this is the best covariance matrix you can get if this is your objective function. So that's the claim. And after the break, there's a very small computation, which is actually a bit easier to do, to also figure out what are the best pi's for this, right? So we have done the mu's, we have done the sigmas, and after the break, I'm going to show you how to maximize the best pi's, and then we have maximized our surrogate. So we have solved the surrogate step. So see you in 15 minutes. We'll continue a little bit. So welcome back. We have discussed the 2 steps. The first step, build the surrogate. Second step, maximize the surrogate. About a small question came up during the break when I'm building the surrogate, so the expectation step. I just want to be fully precise that these Qs are always at time t, and they always depend on the parameter at time t. So just to be very clear, always everything here is at time t. Which kind of makes sense, right? Because the surrogate should depend on where you build it, right? So that's the stuff depending on t. So that's all encoded in the Q things, which we saw that, okay, our motivation for this was just that it's actually an equality and a lower bound it's anyway. So that it's an equality, and we will see in a second on why why this makes sense to build this on the current time step. So, okay. So now maximizing this stuff, we're almost done. How to maximize the surrogate. Yeah, somehow this was a bit a nicer function, and it's mainly because all the variables now are on kind of one side of the log, right? That's the trick, right? So the log stuff outside the log only depends on the red things, which are constant, and stuff inside the log only depends on the actual parameters, the blue theta parameters. So that's why this is an easier thing to do, basically, if you want an intuition for this. So then we tried to maximize it in mu, sigma, and pi. We did it in mu and sigma, and we still have to ask, yeah, which pi is the one which maximizes this surrogate. Okay. Any question on this? Otherwise, yeah. Yes, so you're asking, what if I build this surrogate at the point which is already very good? So I need to redo this picture at the end. So right, so this, okay. The real picture looks a bit like this, right? The surrogate actually goes up, right? Where we currently are, the surrogate is this, but when we maximize the surrogate, we go higher, right? So that's the idea, usually, right? But then your question is, what if we are already somewhere where the surrogate is kind of flat and where we are, so that I think that was your question. What if the surrogate looks like this, then there's nothing I can maximize because I am already at the maximum of the surrogate. So I build it here, and the maximizer of the surrogate is also here, right? That was your question. Yes, this could happen. Then we don't move anymore, so we're stuck. So this can happen, and that's a bit similar as if k-means can also be stuck. So this is a very rare situation. So in reality, the surrogate will always go a bit upward, so that we can improve a little bit, right? But I'm not claiming that this algorithm brings you to the global maximum, right? I'm just saying that in every step it improves a little bit. So you go here, and then I'm claiming that the green function is always above the surrogate. That's for sure, always. So that what that means is that you actually always improve a little bit. Before you were here, now you go here. So you have slightly improved. So that's what I'm claiming. And slightly improved, as you say, it can include tiny improvements or even no improvement. Yes, this can be stuck. So, but usually it will work well. Same situation as k-means. Yeah, one more question. Yeah, there's no proof that we reach a global maximum. The only proof we have here is that we always slightly improve per step. It's exactly like the situation in k-means. There you can also prove that the distances always become slightly better or equal, but you don't prove that you go to the best distances, like distance to your cluster center. There we wanted to minimize it. But it's really the same thing, and I'll show you in a second that, yeah, this is equivalent to k-means in a special case. I mean, special case of this becomes k-means. So we will see that in 1 second. Yes. Okay, but then I just want to finish this small thing, that the 3 things we had to maximize on the surrogate. I think mu was okay, the covariance was okay. Let's see about sigma. This looks like the easiest thing, right? Because it's just there alone on its own as a weight, super easy. So and yes, it is easy, but there's a small but, and the problem is that the pi needs to add up to 1. So there's kind of a small constraint here, right? I mean, we could optimize this naively, but then maybe you get some pi weights which do not sum up to 1, and that would be illegal because we have imposed this in our design, right? The generative model which I assumed was that you must be a mixture of these k clusters, and this mixture weights must sum up to 1. That was our design choice. I mean, at the beginning, you always have to design your probabilistic model, how you model nature. And there we already have made this choice that we have to make the constraint pi must sum up to 1. So let's see if you can respect that here as well. So yeah, I mean, you could think of things like, yeah, maybe project the gradient descent, or so that's what I would do. But here it's actually simpler. Here there is a closed form solution still, even with the constraint. So I'll show you in a second. Yeah.
There was one formula where we also constrained when we were projecting the gradient, and I was wondering how you decide when you use the Lagrangian system and when you.
Yeah, I think you're asking a project gradient descent, right? When I use that, or when do I try to get a closed solution with Lagrangian? Yeah, I have no clear answer to it, but I mean, the big difference is that here we will be very lucky. Here we will get a closed form solution, and if you can get that, then you always prefer it, right? Then you don't need an iterative procedure. It's a closed form thing. If you cannot, then you just use gradient descent, and yes, then you would use projected gradient descent. So that's kind of a more general weapon, right? You can always do projected gradient descent, but then we don't know how many steps and so on. So yeah, thanks. You were asking about the adversarial examples, right? Which is also using this kind of, I don't know. Yeah.
Someone is asking, why do you take the derivative with respect to sigma -1 and not sigma?
Yeah, the question on Zoom, why did I take the derivative with respect to the inverse of the covariance, not the covariance itself? Because it's easier. So because I cannot take it to the original sigma. I cannot take the derivative of an inverse. But I can. But the thing that appearing here, this thing that is sigma inverse, right? So I take the derivative to the thing which defines the Gaussian normal distribution. So that's the only thing I can do. Maybe there are other ways to see the optimizer, but it's kind of easy to take it to the inverse, right? Then you would just get some equation of the inverse will be 0, and it's very easy to solve that equation, right? You don't even care if you have an equation on the inverse, or if you have an equation of the original matrix. It doesn't matter. You can just solve the equation. But I cannot differentiate with respect to a matrix is not appearing, but its inverse is appearing. So yes. Okay, yeah, taking the derivatives as well, these things. So that's actually what I wanted to do. I wanted to take the derivative of pi. So let's just do this naively, right? Just do as usual. But then we will have the problem with the constraint. So let's take the pi derivative to 0. So that's tricky. So what I will actually do, this will kind of violate the constraint. So what I will do is I will replace this thing. Okay, notation is getting me crazy. But I will define this to just be the surrogate I had before, but I will modify it. I will add actually, I mean, that's what this Lagrangian thing means. It just means that I kind of want to add my constraint to my objective. And I do this together with a slack variable. So I have introduced this variable. And here is sum of pi minus 1. I need more space. So, right, the constraint is sum of pi must be 1. And the way I'm going to do this is by adding the Lagrangian term to it. So I introduce a slack variable plus this slack variable times the constraint. Constraint is sum pi k minus 1. Okay. So, and if you do with that one and be careful with the beta, then you can get an explicit solution for this. Again, I will not do the whole computation, but yeah. So what's happening is that you just maximize this thing instead of the original one. And if you do this and you find that this satisfies the constraint, then you're lucky. Then you actually have that you're also optimizing what you wanted to optimize. And we see that this is the case here. The pi's we find, they do sum up to 1. So And yeah. So don't forget that they always must sum up to 1. And that's how we get the update of the pies. So okay, that was a bit of a hack. So to be honest, to come back to your question, I find projected grading much more generic and easy to program, right? So here you have to go quite deep and do formulas by hand to figure it out. And I mean, gradient design would be much more natural. You just throw on PyTorch and let it run and see if it goes somewhere useful. So, but still kind of nice to have a closed form solution. Okay, so I think we have the whole algorithm now. We have designed the surrogate. We have maximized it. What's not so clear yet is why are these crazy Q weights appearing here, and so on. And we will get to this. And is there any question on the derivation here? Then yeah, today was a lot of notation, but it's getting better. We are over the hard parts. So, and also computationally, I just want to emphasize again, now that we have these updates, performing them on a computer is super efficient. I mean, you need to compute a bunch of vectors. It's really, really cheap. You need to average your data, need to compute a few rank 1 matrices. It's all super easy. Here, even easier. So this step is very, very cheap. And the building the surrogate step as well. So just need to compute the Gaussian. So this is quite efficient. Okay, in summary, what is happening here? So there's nothing new on this slide. It's just summarizing what we have done. I showed you the expectation step. I showed you the maximization step. So again, the Qs were defined, and that's what it means to build a surrogate. That's all, and they are defined on the current time point. So at this theta t. So right, and yeah, then that's it, and then you maximize it. So and maximizing means you obtain the new parameters. So this new thing is theta t plus 1, right? And yeah, that's all for this, I would say. You can also, if you want, you can track your objective, see if you made progress. That's kind of what I claimed here, right? So this is the L. I was claiming that every step you do, you slightly improve, or at least you don't get worse. That was the only claim made here. And that follows directly because the surrogate is lower bound and it's identical to U at the current point. So that's all about the EM algorithm. But what I also want to do in this slide, I want to convince you that this recovers k-means as a special case. And that's actually also very easy to see here. So when do we get k-means? We get it when we ignore this covariance business, when everything is spherical. So let's try to do this. So I will just, all covariances will be deleted and replaced by identity. So they become spherical. And spherical means I also need to decide on a width of a cluster. So there's this sigma here, which is, we'll discuss a little bit. So sigma is a scalar, which tells you how wide is your sphere. The width of each cluster. So they're all the same width, right? All the clusters have the same size in k-means. So the claim is if you do this and you let this width to become tiny, so the width goes to 0. So that's happening here. Then the claim is we get k-means. So what is this width, right? It's you can have a Gaussian like this. So then this is your sigma squared. Or you can have a Gaussian like this. that's not a Gaussian. So here you have a much smaller width, and the claim is that when the sigma square goes to 0, then we get the k-means algorithm. But why? So let's see what really happens, right? So now let's look at the equations. So first of all, in k-means there's no probability distributions and stuff. So we just want to see what happens here. So when you plug in this sigma stuff, then you get that the normal distribution now becomes a sphere, and that's what we just wrote before, right? We said that then it just becomes the exponential of the distance from the center. So minus how far away is your xn from where? From the mean, of course. And what else? Yeah, it was divided by the width, sigma square. So this expression, this is just a normal distribution, right? For spherical covariance. And I've just plugged this in. Okay, so interesting. And same here. So here then you have the sum over all k's of the same term. So which is just this stuff from, maybe I'll write it again. So x minus the mean k over sigma square. But yeah, which k? So and now this is where it's getting interesting. So so you can think a bit about like, yeah, which k is going to be the best one here. So here we just sum over all the mean candidates, right? But then here it's about the particular k which is here. So that's a different one. Maybe I use different colors. Sorry. So on the numerator is the k which we have asked, right? Which so with the qkn. So and the denominator is just summing up all the k's. So and what's going to happen here is that if this sigma becomes really small, then this is something a bit extreme happening here. Then I mean these exponentials will become super big, right? Yes. Yes, all of them will, sorry, so this term will be super big, and then the minus in front, it makes exponential super small. So everybody is actually going to be tiny if this sigma goes to 0. So then what happens, right? So then everyone in this is summed up here, and everything is tiny. So the only thing that will survive is actually the one which is not so tiny, and that's the, oh no, I deleted it. So okay, we're back. So okay, so everybody is summed up, and this magnitudes of these terms are very different. So the only one which is going to survive is the one which is largest, which has still a little bit of contribution, because everyone else is much smaller. So what I'm saying is that the cluster, the mu which is closest to you, that one will be the one which has the distance which is smallest here. So will be the only one which has a reasonable contribution. Everyone else is further away from the cluster. So all the other cluster centers are further away from your x. So all those other guys, they have a much smaller contribution to this sum here. So what this means is that this quotient here is going to be either 0 or 1. So and yeah, let me delete this. So when is the quotient 0? When is the quotient 1? That's the question. So this whole quotient will go to 0. So as sigma becomes small, what happens? It either is going to be 1 or it's going to be 0. So and it's going to be 1 if you ask about the closest k. So if this green k here is closest to your x, then it's going to be 1. If k is closest to xn, and it's 0 otherwise. So why is that again, right? So if you're closest, then you contribute the biggest term in the, I mean, the whole thing is going to be the term which has most contribution. So, and then all the terms get summed up, right? But all the ones which are smaller than this particular k, they have much smaller contribution. Actually, they go to 0 relatively to the main one. So then, if you're not the closest one, so if you're maybe the second closest center, if you ask, okay, what's qkn so for my data point xn, which I'm asking about the k, which is the second closest to me, but that one will be completely negligible here. It will just be it will not be the term. It will have a tiny contribution to this sum here. So then this one will be so much smaller than the sum, which also includes the biggest one, right? So I'm just saying this sum here is dominated by the k, which is closest to your x. So with that mu. So that's why the qkn becomes 1 for the closest center and 0 otherwise. And that is what k-means does. So that was the hard assignment. So if q is 0 or 1, then it becomes what we had called z in k-means. So z in k-means. So there was this 0, 1 assignment. So in EM, this can be different from 0 than 1. But if you do the sigma to 0, then you get the hard assignment 0, 1. So you're the question, yeah. So. Yeah, what happens if you have two cluster centers mu which are equally close to your x? Good point. I haven't thought about it. Then, yeah, I'm not sure actually. I think there's a tie-breaking thing here. The argument will still be true, but then you will be like only half of the magnitude is covered by you. So yeah, I'm not sure. Maybe then you need to be more precise to say that you give half to this and half to that. Maybe then it's not clear how to do the hard assignment. Yeah. But we assume that everyone has a slightly different distance, and then it's clear. Then you will get assigned to one cluster. And yes, for k-means, you must be assigned to one cluster. Actually, also in k-means, you have this problem, right? If you're equally close to 2, you need to decide. You can only assign to 1. And that's the same here. So thanks for the question. Yeah. Any other question? Yeah?
What if the sigma is not close to 0?
When the sigma is not close to 0, then I cannot say anything. So then we basically in general EM case, but we have made the shape spherical, right? So you can do that. I mean, yeah, EM. Then you just solve a Gaussian mixture model. So you have decided to solve a Gaussian mixture model, which is spherical, which is fine. It's a good thing to do. So in summary, yeah, if sigma goes to 0, then you get this assignment here, the k-means assignment. So yeah, the q's have become the z's. So I write approximately equal. Okay. And so that's for the z's we have recorded. So what about the other step? And so that's much easier. There it's obvious. So now we have the same process, and we ask, okay, so now how have the parameters, do they get updated? So now I know that what my q's are, right? I know that the q's have become the hard assignments. So then this is directly becoming the mean of the cluster. So it's only in the k-means case, right? Only if sigma goes to 0, that's the crucial So if the queues become this hard assignment, then again, you are fine because you get, I mean, you get the same as in k-means. The sigma, there is no such thing. And then the pi's, well, yeah, they do sum up to 1 because also the hard assignments sum up to 1. You can only be assigned to one cluster. It's a 1 for the z variable. All the others are 0. So yes, again, they do sum up to 1, so things are fine. And so, sorry, this actually is counting the number of points assigned to cluster K, right? We're just asking who is assigned to cluster K. There might be number of points assigned to cluster K. Okay, so all that to say that if covariance goes to very, very small and is spherical, you get k-means. So that was the purpose of this slide. And if there's no question on it, we have 1 or 2 more slides to discuss. There is a slightly more general version of the EM algorithm as well. So almost done, but it's kind of nice that it's a generalization. So also to get a bit of an intuition what's happening. So the picture is really almost the same as we have seen in k-means. So let's run it for real. And I think this you can also do in the lab next week. So there's again this kind of 2 kinds of steps. So maximization. So of course, I mean, first the expectation step to build a surrogate. So here is the E step, which you do first. So the E step means to build the queues, which you can think of as these. The queues are the soft assignment variables, right? Because they correspond to the k-means hard assignment. And I'll explain you afterwards why this is a soft assignment, why this makes a sense. But the queues are like the assignments, right? So what I'm plotting here is actually for every point there is a queue telling you that you are 30% red and 70% blue. So that's what the queue is, because it's QKN, right? So that's what these colors here mean, right? The points in the middle are a bit 50-50, they are purple. And the one here is a red point, which is like 99% red and 1% QN for blue. So that was the E step. And then we have the M step to maximize the surrogate, and maximizing means we change the parameters. So we change the shapes and positions of the 2 centers. So this is how we update our GMM, right? The Gaussian mixture model. So we have 2. Here we're doing a mixture of just 2 Gaussians, so very simple. You need to, of course, initialize it somehow. So usually you initialize them spherical and somewhere. So, and here is the first time we changed them. So now they have become a bit ellipse. So this is from the sigma update. So now it's actually present. This is not k-means. Here we do the real thing with a real sigma matrix. So that's why they have changed the shape. Then they also have changed position. So that means that the mean has changed. And that's it. So finally, we do another E step. So we recolor all the points. So that means the new, the Q guys have been computed, right? And then another M step. Okay, and yeah, the result seems a bit similar as in k-means. The only difference seems that the shapes of the cluster now can be real ellipses, which is nice, because you can see maybe this cluster is not so well approximated by a circle, but it is well approximated by an ellipse, and the algorithm has found it. And yeah, you just perform as many iterations as you have patience to do. And that's it. Yeah. The arrow, it would just mean to perform the step, right? So here is before the step, here is after the step. So it's just time. I've done 2 rounds. So EM is 1 round, and then here I have stopped. So. Oh, sorry. What you asking? What is the L in the graph? So, good question. So, yes, but yeah, ignore the L. So because here I was just want this is iteration 1, iteration 2, iteration 3. So just think of that. So, and yeah, in EM it's not so clear when to stop. It's in K-means it's more clear because eventually your clustering will not change anymore. Here you will probably keep changing a little bit forever. So yeah, maybe they stop this after 20 steps. I don't know, but it doesn't matter. This is for illustration. How this would look in practice, and play with it. Try it out in the lab. There's a very nice Python notebook. Okay. Okay. So and now finally, I guess you and also I still feel a bit uncomfortable about these Q things on why the hell were we setting them to these strange values and so on, and what are they actually? And so finally, I can give a little bit more insight on this because they have a very nice interpretation. They are very clear. They have a very clear probabilistic meaning, and it's a bit what this feeling we had here when we said that you are 70% red, 30% blue. That has a formal definition, and that's here. So it's here. The Q's exactly mean that. They mean that. So here is the hidden variable z that you are assigned. You're either red or blue. So, and they're exactly giving this probability for that happening. So, probability that the point is red, or so K is red or blue, given that you have this data point and the current parameters. So, what is this? This is like a hidden variable conditioned on the data and parameters. That is a bit strange. What we are more familiar with is actually something like this here, the probability of the data given the parameters. So that's something that we know. So, and this is a likelihood we know. The stuff on the left, we also know. This is the joint, of course, the joint distribution. So X and Z given the model. So this we also know. This is the prior we have on this hidden variable. But okay, none of this stuff is what we have here in blue. So what is the blue thing? And this we can understand also. This equation here is just Bayes rule, so nothing has happened here. So here is the quantity we're interested in. So it's on the right of the equation, and that thing is called the posterior. So and then on the right we also have the probability of X given the model. So here the Z's have disappeared, and that quantity we have also seen before already. So I'm just giving you the name. So this was what we call the marginal likelihood. So I mean, all the quantities we already know, except the blue one is the first time we see it. But the good thing here is that yeah, the other ones are nice to understand and so on. And so just to make a bit more clear why this equation, so this is really simple. So this is just a probability of A given B, probability of B. So this is just talking about the Z's and the X basically. So that's this, and then on the right we have probability of B given, sorry, maybe I write it here. B given A and probability of A. So just by Bayes rule. So forget about the parameter. That's not what this equation is about. So not about the theta. because that's conditioned everywhere, so we can ignore it. This equation here is about x and z. So it's using base rule on x and z. And it's just telling you, yeah, it's not telling you much actually. It's just telling you how they're related. It doesn't tell you yet that the q is actually equal to this. But that's gonna be our next step. So I will try to convince you. So let's use this knowledge. I mean, this is just giving names to stuff and nothing happens. So the only thing I'm suggesting here is to apply base rules, hopefully to understand this guy, to understand this term. So let's see. I will solve this equation now for the posterior. That's what I want to study, right? So I want to have this on the left side. Posterior, xn and the parameters. So it's just going to be this thing divided by that. Prior times likelihood divided by the marginal likelihood. And yeah, that's the last formula we have to go through today. And then things are good. So the prior, we are very clear what it is. So that's actually pk, pi k, because that's exactly how we define the prior. Okay, I write it in two steps. So probability that Zn is equal to k, given the parameters, and that we know, we have defined this. So that was our very first design choice. When we did Gaussian mixture model, we designed this was designed to be pi k. Okay, what's the likelihood? We are also familiar with that. X given z sigma, sorry, theta. And then again, it's summed up, or pi k, which is, so now I'm dividing by the marginal likelihood. And there again, the point of the marginal likelihood is that the hidden variables disappear. So I'm actually taking an expectation here of whatever these sets are. I don't know what they are. So I just average them out. So set n equal to k times the likelihood. And again, this thing is just a pi k. Okay. And then about these guys, well, they are just these are the easiest ones. So these are the normal distributions of x, normal distribution of x given the parameters. Okay, so all this is just to say that yes, this is q and k. So just by how we have designed our probabilistic model, it's very clear that this, I mean, before we were not clear to us why we chose the q and k's to be this, but now we know what they mean, right? So they mean to give you the probability that you are assigned to cluster k if you are data point x and the parameters are like this. Does this make sense? Good. So this seems to be a nice recipe, right? So what we have done here is just computed these q's to be kind of the averaging out what we don't know. So we don't know the z's. And then this helped us to define a surrogate. So there is exactly the same thing. You can do much more generally. So that's exactly what's written on this very last slide, promised. So that's what's written here. So here there's a very general probabilistic model I don't know what it is. It has data and it has hidden variables x as z. I don't know the z's, right? They're hidden. So of course, what you've done so far was an example of that. But now what I'm saying is that here I should just take the expectation over this hidden variable set, whatever they are. I don't know what they are. I would just take the expectation over them. And that's what we did when we computed the marginal likelihood, right? So because you can see this thing here is the likelihood p of x and z together given the parameters. So what is happening here is that you just average out what you don't know. So and that this expectation here together, this is the surrogate. So of your current parameters theta. So this is a generic way to build surrogate. Whenever you have a probabilistic model, you have hidden variable z. It's just you just do like this. You compute this expectation, and you can see the expectation is computed at the current time t. So you don't know what the sets are, but the best guess you have is that they will influence the model like on average, right? So things will just be like on average over all sets. So I will just average them because I don't know them. So then I have this thing here, which is my surrogate. And then I maximize it. And that we familiar with, right? That's what we always do. And that's our next iterate. So this is the much more general form of this same algorithm. And this is really the same thing as we've done the whole hour now. So you can see we have averaged, and this expectation, these averaging weights, these were the Qs. We've averaged this simplified function, and then we have maximized it. So it's a very nice thing to do to deal with uncertainty. You don't know what the sets are. So one way to think about it is just think that these sets, you can think of them as being part of the data, but you don't observe it. So it's kind of a hidden part of the data. And then it can also be reasonable to just average over it. So, and yeah, that's maybe the simplest interpretation. Or you can think of them as the latent variables, right, as we did when we introduced the Gaussian mixture models. So don't worry, either way is fine, right? You don't need to, it's not the one way it's correct or it's wrong. Like either you can, the sets can be hidden parts of the data, or they can be hidden parameters which you would like to optimize, but you cannot. And then the natural thing to do is to just average them out. And that's what it means to build this surrogate. So it's actually probabilistically motivated. All right, this is all about EM. And next week we change to generative adversarial network, also known as GANs. So see you next week.